Hey, AP Chemsters, this is Mrs. Vanderwall bringing you another edition of the Blank Wall series. And right now we are starting with section 17.8, the free energy changes for non-standard states. You might want to go back and look at what we have done already and the meaning of delta G. That's where this comes in. Delta G is the Gibbs free energy. It determines the spontaneity of a reaction. Does it go or not? If delta G is positive, it is said to be non-spontaneous. If it is negative, it is said to be spontaneous. If you go back and look at prior work, let's kind of go back here a little bit. What happened here? We were calculating the delta G naught prior. This was way back in like second semester of the delta G of the reaction, and there's a little circle on the top there. And what did that little circle mean? That little circle meant at standard state. Now, how often are we at standard state? We're not, okay? So what this next section is how to calculate Gibbs free energy if we are not at standard state. And we're gonna revisit our old buddy Q again. Remember Q from chapter 16 where we said, will the precipitate go if Q is less than KSP? Similar idea here. So again, the standard free energy change, here's a delta G naught. Again, very narrow set of conditions. They're in their standard states. How often does it occur? Not very. So let's check out this example of what we're talking about. In your heart of hearts, do you know that liquid water will evaporate to make a gas? Yes, it does, all right? It's raining actually right now, and the sidewalks are full. There's some puddles out there. I bet tomorrow when the sun comes out, there will be no puddles left because it evaporated. But hang on, look what delta G naught is, a positive 8.59 kilojoules per mole. So at its standard state, it is not spontaneous. But we do know water evaporates, so it is spontaneous. So how do I deal with that? Well, let's check out. We have a new equation. Delta G at its non-standard state is equal to delta G of its standard state plus RT ln of, oh, here's our buddy Q. So Q is the reaction quotient. Going back from chapter 14, we did it some in 15 and we did it again in 16. And for gases, we want to use the pressure. For solutions, we want to use concentration. R is the gas law constant for 8.314. Don't use the 0.0821. Delta G naught is the free energy where, oh, look at this, where the pressure's at 1 atm. And delta G without the naught is when it is at a different pressure for gases in this case. Now let's go back and look up here again. So if the pressure above the liquid is 1 atm, hey folks, that's where we said it actually boils. If you go back and look at that chapter there of gases. So if the pressure of the liquid water here is at 1 atm, it doesn't evaporate, it will boil away. So that would be a different set of circumstances. But what about at normal, like looking outside and looking at my puddle? Is the pressure really at 1 atm? The answer is no, it's much less than that of the pressure of the water vapor above the liquid. That's the pressure we're talking about. So let's go and actually look at this example and see how we actually calculate it. So here's our same setup of liquid water evaporate into gaseous water. Delta G is a positive number. Here is a really helpful graph, if you will, where it talks about the delta G, the Q values and the pressures. So notice right here where pressure is equal to 1 atm, Q equals 1. Where pressure is at equilibrium is 0.0313 atmospheres, it looks like. So really the water vapor above the puddle, if you will, has a very small vapor pressure. And anything below that 0.0313, all right, including the 0, okay, will have, this section. Delta G is negative here, delta G is 0, delta G is positive. So let's check this out. It's standard conditions. So when it's G naught, what was our pressure at standard conditions? It's at 1 atm. All right, so we are looking at right here. Pressure is 1 atm. We have a lot of water vapor above the puddle. So here's our equation. Hope you're writing this down. And so what do we know? We're solving for this. We're trying to see if delta G at our conditions is positive or negative, see if it works. This is what was given to us at point 89 kilojoules per mole, RT, L, and a Q. Well, what's our Q? Well, if I were to go back and look at Q, isn't it products over reactants? But do we ever put liquid in our Q expression? No, we don't. We only put gases in there. So we only have uh, 1 because it's at 1 atmosphere. So it's not 1 squared, it's not 1 over something because it's only the gas pressure. We don't count the liquid. So folks, you notice something. We're using the natural log. What is the natural log of 1? Go ahead and plug that in your calculator right now. Here, I'm going to pause this. Go ahead and do that right now. Get out your calculator, and what is the natural log of 1? Well, isn't it the same thing, the log of 1 in this case? All right, and it's 0. So if the natural log of 1 is 0, then I don't really care what RT is. It's all going to be equal to 0. And so what am I left with? Oh, okay, positive 0.85 kilojoules per mole. So it is not spontaneous. So if we pick a non-standard condition, any pressure other than 1, all right? So I've just made something up. So if we have on a dry day, pressure could be 0.001, all right? So let's make this Q value 0.001 atmospheres. It's a dry day, might as well. So let's go ahead and check out our equation. Here it is. So, oops, sorry about that. We know what delta G is. Oh, I'm sorry. Put that in here. Delta G naught is 8.59. I actually plugged in my, I'll stick over here, my 8.314. Here's my temperature. If you go back and look at our temperature for this, all right, we'll just say it's 25 degrees out, which is not unlikely, and natural log of 0.001. Now, will you go ahead and pause this and actually do your math and make sure you're using the natural log, not the LOG. Go ahead and do that. Okay, so hopefully you get this. And what's my final answer? I guess I don't have it plugged up. So it looks like a negative 8.6 or something. So notice you have a negative value. If you have a negative value, oh, there it is, negative 8.5. If you have a negative value, is it spontaneous when it's a dry day out? Of course, my puddles are gone. So that makes sense to me. Let's go and check the next part here. Oh, by the way, I just want to show you, what about at equilibrium conditions? So what happens when the pressure is 0.0313 atmosphere? So I went ahead and plug this in again. There's my equation. And here is my, notice I have the natural log of 0.0313. You go ahead and do the math yourself. Make sure you use natural log. Hopefully you got this. Notice that this term right here ends up being negative 8.29. Oops, sorry about that. And notice what we get here, 0. Okay, it gets 0. So that's equilibrium. Oh, just like what we've been talking about. All right, when the rate of the forward reaction equals the rate of the opposite, that's 0 delta T. Okay, let's go to the next page. All right, so here is your chance to see what happens when the pressure is a different one other than equilibrium, other than standard. So why don't you go ahead and set up this, actually do it, just don't watch me do it, you try it on your own, and see what you get for delta G at pressure equals 0.0050 atmospheres. Do the math and come back and see how you did. Voila! All right, so here is your work. Notice that it's negative 4.5 kilojoules per mole. It's negative, so is it spontaneous when the pressure above the puddle, if you will, 0.00500 atmosphere? The answer is yes, it is still spontaneous. Let's look at problem number 12, see what we do here. Okay, so consider the reaction. They were giving you the delta G naught here, and now we have pressure of NO, pressure of O2, NO2. What's going to happen is it going to be spontaneous given these conditions. Notice that none of the pressures are 1 atmosphere. They're non-standard. What is delta G of this reaction? Okay, well, all right, let's check this out. Oops, sorry. Here is my equation. And next thing I need to find is the, plugging in some numbers here. Notice I haven't figured out what Q is. Do you remember what Q is? It's products over reactants. Look at the states of matter. We have gases, so they all can be used. So, okay, I'll start figuring out Q. Q is my products. Notice I had to square it, so it's NO2 squared over my reactants. I had to square my NO as well, which I have right here. and I just plug in oxygen. So if you do your math, go ahead and use your calculator and see what Q is equal to. Okay, hopefully you did it. If you need to pause it, go ahead. And I got 4,000. Hopefully I did it right. And so now, what kind of number do you get when the natural log is 4,000? Is it a positive number or a negative number? Hopefully when you do the work, you'll see it's going to be a positive value. The question is it so positive that it overcomes the negative 71.2 kilojoules from non-spontaneous or not? One other thing to notice, this is joules. This is Kelvin, and this is no units. What we have to do then, if we want to add these two terms together, we must convert joules to kilojoules, divide this whole term by 1,000. Okay, and this is what I get. Notice again, it's positive 20.5 kilojoules because this natural log is a positive number. And if I added all that stuff together, I get a negative 50.7. So it is still spontaneous given these non-standard conditions. Okay, I'd love it if you do problem 13 on your own. A couple things. This is a gas, not a solid. Can you please change that? And the notes didn't give you the delta G of the reaction. So it is negative 102 kilojoules. So go through, pause this please, do your work yourself. Just don't watch me do the work and copy my work down. Actually fill out your stuff and see how you do. Pause this. All right, see how you did. Oops, I guess I have to extend the page here. All right, here we go. So there we go. Here's my equation. Here's Q. I solve for Q. Notice what kind of number this is. This is a really small number. Notice the natural log of this itty bitty number, it's going to be a negative number. So if this natural log is a negative number, then these values are also negative. So you have a negative 27.3. Well, it's kind of like, well, no, duh. If you have a negative 102 and a negative 27.3, then yes, we have a negative delta G of the reaction. It is spontaneous. Let's see what happens in the next problem. When, look here, I don't give you the delta G of the reaction. You might need to go back and see what we have to do. All right, I spoke too soon. I forgot we had problem number 14. Oh, remember our buddy Le Chatelier. Okay, so we still need to worry about Le Chatelier. He comes back here. According to Le Chatelier's principle of dependence of free energy on the reactant product concentrations, which statement is true? So high concentrations of reactants relative products result in a more spontaneous reaction than one where reactant products are under standard conditions. Would you agree with that? And that doesn't sound too bad. Let's see what the next one is. A high concentration of products relative reactants results in a more spontaneous. If anything, if you have more products. All right, so if you have a high concentration of products, that means Q is really, really big. And so what's going to happen if Q is going to be greater than, let's say, the equilibrium, what's going to happen? Q is going to be a positive number. So net log is a positive number, and it may be so positive that delta T becomes positive, and it's non-spontaneous. If anything, it's going to go backwards. So what about letter A? Let's go back and kind of look at it here. If you have a high concentration of reactants, what happens to Q? Q gets smaller. So if Q is smaller than the equilibrium in a sense, that you have a negative natural log. So if it is so negative that it's going to, make the whole term be negative, then yeah, it is spontaneous. And a reaction they're in the standard states and no products are formed, then it's more positive. That doesn't really make a whole lot of sense because your natural log is going to be 0, the whole term is 0, they're going to be equal. So my answer is A. All right, I do want you to look at this. Okay, what's going on here? We have, I didn't give you delta G of the reaction. I gave you delta G of the formation. Here, go back a couple pages. Oh, do you remember this? All right, delta G of the reaction is a summation of the products minus summation of the reactants. You might want to go back and look at that again. Because I gave you here the delta G of formation. So you actually had to use that equation again. Go ahead, pause this, and come up with delta G naught. Okay, hopefully you got this. You have products minus reactants. Notice that hydrogen is in a standard state, so it's 0. So we ended up with negative 29. Now it's just like all the other prompts. Go ahead and do it, and I'll share the answer in about a minute. Here's the answer. Pause it.